Hello. So let's continue the lecture. As you people know, कि I have a office also. So managing the office hours with the lectures, it's tough, but still I'm trying to do all those stuff. Nothing should be left, you guys. Chalo. So let's continue the lecture. Fundamental theorem on homomorphisms or of homomorphisms. What the theorem says is statement every homomorphic image of a group is isomorphic to a quotient group. Please do remember this statement. I have already used this statement to make you feel, to make you visualize the things, how this fundamental theorem is useful. See, as the changing pattern of this CSE exam or IFS, they are focusing much on the concepts which I dealt earlier, finding number of homomorphisms. Okay, finding number of, bit like analytical you can say. Okay, earlier before 4 to 5, like 3 to 4 years, what they used to do, they were focusing on the theoretical theorems, proof and all. Now the pattern is being changed a bit, but as an aspirant we must take care of both aspects. So the pattern which is going on now, that already I have discussed with you, this is the thing which also you have to prepare for worst scenarios, because in this CSE exam the first tagline is be ready for the worst. That clear? Chal. Also from this statement, I will try to give you some learnings that how we can approach proofs in an easy way. Okay. So let's say we are going to use, we are going to prove this theorem. As I earlier told you, in abstract algebra, proofs are easier to do once you are clear about the definitions. Please mark my words. And if you are able to bifurcate your statement in a smaller segment. So please be on the board. This proof is gonna be a model proof for you guys. Okay. What it is saying? Homomorphic image, okay, of a group. Isomorphic to some quotient group. Ultimately, I have three components here in the statement. So number first is I have some homomorphism from a group G. Let's say if it is onto homomorphism, that means image of phi is equal to G dash. Okay, the range of phi is G dash because this is onto. So let this is a homomorphic image. So first component, ki every homomorphic image of a group. So let's have this homomorphic image as image phi. Okay, I have to show this image phi is isomorphic to some quotient group. Okay, this is our target. That means In the second step, I need to find that quotient group. Okay, that is the second step. And third step is to define a mapping F from where? Image phi to GK or F such that GK to image phi. This I have already told you guys. To prove that two sets or two groups are isomorphic, we need to find a mapping which gives operation preserving 1 1 and not. Is that clear? Fine. So this is my step third. What I do for step 2, what is my step 2? I need to find that quotient group. Okay, since be on the board please, phi G to G dash be a homomorphism. Okay, if it is a homomorphism, then we will have a subgroup of G as kernel phi, means collection of all those elements which are mapped to identity element of Z dash. Kernel phi, let we represent this kernel phi as by K. Since the kernel phi is normal subgroup of the domain wala group, this implies we can have a quotient group as GK, because to define a quotient group we need to have a normal subgroup of that group first. If this K is not normal in G, we cannot define a quotient group. So step 2 is clear. Any problem? Fine. Now coming on the step 3, to show that this F is an isomorphism, let's define F. Please be on the board. Let's define F by the formula F is from where to where? GK. So what I told you dear earlier, we use the identity of the group to define that formula. So what is this? This is nothing but collection of cosets of K in G. What is that quotient group? Collection of cosets of K in G. So let's say I have a coset KA. Okay, and we map this Ka because elements of this GK will be of the form Ka, Kb, Kc, coset C तो होंगे इसके अंदर. So what I do, I define F like F of Ka goes to phi A for A belongs to group. Be on the board and take it very serious. Phi of A, ये किसके अंदर जाएगा? Image phi के अंदर जाएगा कि नहीं? It will go. It is an element of image phi. And phi is what? Phi is a homomorphism from Z to Z dash. So this K will be element of G. Any problem? Now, our task is to show what we have to show. F is operation preserving, means F of KAB, is it, or F of AB? F is operation preserving, means F of composition of two elements, of the domain is same as F of KA composition F of KB. So what we can do? F of KA. From here, please be on the board. F of some element giving me phi of, tell me, AB, because product of two cosets is defined as KAB. This I told you earlier. HA composition HB is equal to HAB. Do you remember? So KA KB is same as KAB. So KAB will be defined as by this formula phi of AB. This is phi of A. This is phi of B. Since phi itself is a homomorphism or not, what I have taken, phi itself is a homomorphism, so phi of AB will be phi of A, phi of B. So what we have shown here, LHS equals RH. Any problem? Number second, this F is 1 1 and number third is F is on 2. So 1 1, how we show? We take two images as same. If F of KA equals F of KB, so F of KA is what? Phi of A. This is what? Phi of B. Is it or not? And phi of A. Now here, if A equals B, then KA must be KB. If KA must be KB, then F of KA will be equal to F of KB. How I used this? What I used here? Properties of cosets. Any doubt? If you have any doubt, do revise the lecture where I taught you properties of cosets. Since phi was an onto homomorphism, that means in image phi, each element A will have its inverse image in the GK. Let's say there is some element B, so corresponding to that phi B, we can write a coset KB. What it is implying? This F is onto. You can write in words also, for each element in phi A, we can have a coset in GK. Getting? Such that for that coset the image is phi. So this is a very important theorem for you guys. You can take a screenshot of the whole picture. This is a model proof for you. I already told. To learn how easily we can do. In the books, if we see the story, our mind will be boggling always. Yeah, what rubbish is this? How I can do the proof? Proofs are easier if you are able to recall your definitions, if you are able to bifurcate your statement, and if you are able, what does actually some statement means, what does isomorphism means, how I use the identity means the recognition or the definition of the set to define that formula. So this is for you. I have tried my best to make you able to make you comfortable in doing proofs. Rest is your choice. Okay. So you have taken the screenshot? Fine. How it's gonna be useful? From this statement, from this fundamental theorem, if somebody asks how many cosets can have a group, or if you want to show how many such homomorphisms you can define, earlier we have done this question. So this fundamental theorem is very useful. If you are not still getting what is important, then do watch the starting of this lecture, how I used this statement. Okay, so very important for you. So the next part is same lecture only. Automorphism. Important. You can have a question from topic. So the number first part is definition. What is the definition? Write the definition. An isomorphic mapping of a group G onto itself. What is it? Isomorphic mapping from a group to itself means the restriction is, earlier we are taking G to Z dash, G dash may be any other group, but in case of automorphism, what is itself. So this is an isomorphism from group to itself. Is that clear? It is very important for us because there are some results which are used to prove something else, like fundamental theorem, like isomorphism theorem. This automorphism is also gonna be very useful. So for this, let's try some examples. Let's have a identity mapping. So identity mapping is what? Which sends each element to itself only. I want to know whether it is an automorphism or not. For automorphism, what I have to prove? Number first, I of AB. That must be equal to I of A. I must be 1. I must be. So I of AB is defined like this. Here I of A as A, I of B is, so LHS equals, let I of A equals I of B. This implies A equals, so yes, it is 1. 1, 2. For any B belongs to codomain wala group, there exists some element in G such that I of that element is B. If the element of the codomain wala group, some element of the domain. What is this is an automorphism. Other example you may have. Example 2. A. You want something? F such that G to GS. Just wait. मैडम चाहिए क्या? G to G defined by f of A inverse so that it is an automorphism. Easy only. Let's say you want automorphism. So f of AB must be equal to f of A, f of B. F of AB from this map formula, what will be? AB inverse. This will be A inverse, A inverse. So AB का inverse in a general group is B inverse, A inverse, and this A inverse, B inverse. Do you know? Crazy है. They can say, okay, हो गया. No. If G is not abelian here, then this is not operation. Now, if G is abelian, then what will happen? B inverse A inverse can be written as A inverse B inverse. In that case, LHS equals next is 1 1 and 1 2. ठीक होता है. And here, if it is inverse, then it will be inverse element from this side. So you can write this inverse will have its inverse here because A inverse ka inverse is A only. So that is 1 2. Is that clear? Let's move to something next. Let G be a group. F is an automorphism of the G be a group, and F is an automorphism of Z. N is a normal subgroup of Z. Then prove that F is a normal. Automorphism. The next concept is group of automorphisms. So dear, F is mapping from Z to Z, not only mapping V and automorphism. Means F is isomorphism from Z itself. F2 is another automorphism. Similarly, F3, F4 and Fn is also an automorphism from G to G. So what we're gonna do is, let's have a set with collection of all such automorphisms. F2 dot respect to composition of what it is of collection of all our possible automorphisms from a Z onto Z itself group. Although I have already told you, we can define a mapping from G to such that identity mapping. Okay, I will be the element of this thing. These are mappings. Follows associativity. So if F is from G to Z automorphism, then you can also have a mapping from G to Z. As I told you earlier also, A is equal to A. G to Z again it will be an isomorphism. That means for each F involve is also an you can set the operation. For that, what you need to do is closer. If any two arbitrary elements, let's say Fi composition Fa, so again an isomer element of S with respect to the compositions is closed or composition binary. You getting my point? The proofs of all theorems, statements which I have discussed here multiple times that I don't want to for you. Just give you ways to think, because how to think, everything is gonna be other. Okay. G is a special symbol which represents in the assignment report you will result something like order of G is n or something like relation between UN and G. UN is just collection of relative primes to n. Okay, think over it. We will be discussing this in our this exercise wala. Okay. Here is automorphism. Just first is homomorphism and isomorphism, then automorphism, then inner automorphism. Will be an automorphism or will make some actually this is also very important terminology for UPSC guys. Some where they can ask the question from this theorem. Actually, our target P is what? Center of G. Is isomorphic to IZ. Is it visible to you? G is isomorphic to, some people write this also. Anything. Now we are going to study inner automorphisms. Inner automorphisms, collection of all inner automorphisms will be represented by set in G. Then we will have a theorem that GZ is cyclic to inner automorphism. Used to calculate some problems, like in the starting of the lectures how we studied for the same fashion. This is also used. Before that, I will suggest you to do the proof of the theorem also, very much expected in our exam. Just how this can be. Definition of the definition as, let be a group mapping, let G be a group, then a mapping inner automorphism F A inverse XA. Please do remember this definition. A special automorphism for which the formula is FAX A inverse XA for all X belongs to G. Just to simplify, suppose that G has n elements, A1, A2, AN. When I say FAI of A1, let's say it is defined as AI inverse A1 AI. FAI of A2, that means AI inverse A2 and AI. Now it will be clear, because what it is saying here, what is the definition of it all about? So the definition is like this. Any doubt? I proved the earlier theorems also, so you can go to proof. Now it's your chance. I will suggest, please do this proof by yourself first, then see in the book. What you have to show? This is operation preserving 1, 1 and 1. You are done with that. I'm interested in defining a set, suppose that as inner automorphisms of G. That means that is a collection of these FA1, FA2, FAN, where these FAIs are different. This. What this is that this inner G with respect to composition of functions is also a group. Getting in the same you need to the element. Tell me, identity mapping, how the inverse will be defined. Okay. To remember this statement, each of the thing will be clear. What is. So the ultimate part is, this is a group. Is it? Check it out. I'm just interested in proof for This is very important. Only. So ZG isomorphic to inner this to what I said, how to proceed. We find a formula. Now I guess isomorphism. Why? How? Using पहचान. That means recognition of the group. किसका? Z, Z का. Z, Z. What? Center of G, and also we have proved that Z is normal subgroup of G. So we can define Z, Z. What is the पहचान? What is the F A X that goes to A inverse X A for all X belongs to. So how you are gonna use of these Z will be looking like ZA1, ZA2, Z. Let's see. So where A1, A2, AN, those are elements of phi from Z to Y. Can I just define this formula phi of Z as FA? Please think over it. How you use the identity, like how the definition of the set itself. Here it is a question mark whether it works for you. Once you are in the habit of doing this now, again I will repeat, everything is going to be whether I is preserving or not. Preserving will be phi of ZA ZB. So these are just cosets. So coset, this will be phi of Z. Phi of ZA will be defined at F. FA is a home inner automorphism. Homomorphism also. This will be operation preserving or not. Talked to also. So these are some definitions which are very, very important for you. You need to do all this exercise, dear students. One thing I have today, patience please. In the Galleon also, in any book you are following, there will be some theorems regarding these homomorphism, automorphism and inner automorphism. The general thing or the important things or from where the concept may be I have discussed for you guys. Where you can suffer, those things I have already detailed for you. Now it's your part, it's your turn to do that exercise, to do those theorems. If you suffer any of it, let me know. surely try to resolve all those things in the getting. So I will this is the lecture for this homomorphism part. We will be discussing about fundamental theorem for finite abelian group, product of subgroups, general stuffs which are also useful for your exams. So stay tuned. Discuss the next part.